Hello! Today I'd like to talk to you about vectors and scalars. Alright, and so when I hear the word vector, of course my mind immediately goes to the movie Despicable Me, and I think of the character, Vector, the antagonist to Gru. And when he introduces himself to Gru, he explains that his name is Vector, and he explains that the reason his name is Vector is because he's committing crimes with both direction and magnitude. And so that's the definition of a vector, and that's why a vector is different than this word scalar. And so this video is intended for high school honors physics, and so the assumption is that you've already had algebra 2 and you have not yet taken calculus. And so this is not a calculus-based course, but we're integrating vectors into this to help create free body diagrams so that you understand why we are doing free body diagrams.
And I haven't explained what a free body diagram is yet, but I just want to make sure you know that I'm going to explain that in this video, and we'll talk about a few other things that you haven't learned about yet.
All right, and so in this discussion, your objective as the student will be to be able to explain what is a vector, what is a scalar, how are they different, and why are they used. So you as the student, I want to challenge you to not only understand these concepts, but be able to explain them to somebody else. All right, so anyway, a vector. A vector is a mathematical quantity composed of magnitude and direction. A scalar is different. It's only magnitude. It's only magnitude. And so here I have a list, as you can see, of vectors and scalars. And I've highlighted ones that are similar, and then the other ones aren't necessarily similar. They might be related through equations, but starting off with an example.
Force. So I'm going to start with force because force can only be a vector. It can't be both a vector and a scalar like displacement and distance can be. So I'm going to start off with that example.
See, I'm pushing on a refrigerator. Let's let this box here represent a refrigerator. And if I happen to be pushing on this refrigerator, I might express my push in newtons, which is force. So if I'm pushing with 100 newtons of force, it doesn't make any sense for me to not tell you which direction. Okay? I have to give you the direction. In this case, I would be saying I'm pushing it. Maybe this is your house, and I'm pushing it in the doorway. That would be a vector. So if I'm pushing it into your house, you know which direction I'm pushing. And in this case, the magnitude of my push is 100 newtons. Say that's not enough to get it to move, right? So we need help. So you have another person that's maybe pushing. Maybe you ask your kid to come and push. He's not quite as strong as you are, but you know that if he helps you, you can probably still overcome friction or whatever's keeping it from going in the door and get it into the house. In this case, your force vector might be represented by this arrow and this 100 Newton force magnitude. And then your child or whoever's helping you is pushing with 50 newtons. And these actually aren't very large forces, by the way. But just for the sake of this example, 100 plus 50 is obviously 150. So we could also represent the combination of these two vectors as an arrow that's roughly the sum of these two lengths. Okay. And this is why it has to be a vector. You have to have a direction. So anyway, if I wanted to be as concise as possible, I would just consolidate these two vectors. So maybe combination of our forces gives us a total force of 150 newtons, represented by that arrow with that direction, and the magnitude represented arguably redundantly with the 150 and also with the length of the arrow. And you could probably put a scale here, maybe that much arrow is equal to 100 newtons. And so you know that if it's 1.5 times that length, it must be 150 newtons if you wanted to make a scale for it or something. And you actually see these on maps for displacement. They'll have a scale and they'll kind of give you an idea of how far away things are from each other. So if you've ever looked at a map before, I believe the GPS iMaps app on iPhones will actually have a scale in the bottom corner. I kind of have a fleeting recollection of that, but I don't know for sure, so forgive me if I'm wrong. All right, so here's an example of the difference between displacement and distance. I want you to imagine for a moment I have this object here. I have this object here, and I'm going to move this object to the right. Move this object to the right 1 meter. Okay, so moving this object to the right 1 meter, this would be a vector, and this would be considered displacement. If I only told you I moved the object 1 meter and didn't tell you which direction, that would be considered a distance. The reason this is useful to have a displacement is sometimes we will want to acquire a velocity. We might also want an acceleration. And these pieces of information are very useful if we know how long it took us to do these things. So for example, if it took me 3 seconds to move this box 1 meter to the right, let's say it took 3 seconds. 3 seconds. Velocity and speed are both distance over time. So if I only wanted to express this as a speed, I would put 1/3 meters per second. That would be my speed because it took me 3 seconds to move 1 meter. Okay? But if I wanted to express this as a velocity, I would say that I moved 1 meter to the right in 3 seconds. And so that would be 1/3 meter per second. And you can either draw a vector to that direction, or you can write to the right. As long as you indicate the direction, as long as you include the direction and the magnitude, you are giving a vector quantity. Okay? In this case, we have displacement, we have velocity, and I'm not going to go into acceleration in this particular video, but you get the idea. I hope that helps. I hope you learned something. Thanks for watching.